that you can start off.
This meeting
Or
is
maybe,
being recorded.
or we can take partitioning, which is the next topic after the leaderless replication. This is thing ending over here. I don't know how far. I don't think we are very far. It's like we are on page 179 right now. Uh, it's 181 and then 181 going. Okay. Yeah, there's a bit more. Okay. Oh, I mean, I don't see it finishing today, that's for sure. A good amount of 10 pages more. So, what you can do is maybe you can plan for partitioning. That will give you enough time also to prepare by the time we finish leaderless replication. Does that work for you?
Yeah, that works for me. So how many days can leader application take? Maybe 2 days, right? So I anyway go with
Minimum two
subtopics. So
days, 2 to 3 days,
yeah,
because
all right.
today we are going to start with page 181. 10 pages roughly, I mean, depends on the conversation we have. But definitely 2 sessions will consume.
Yep, sounds good to me.
Okay, so welcome once again, everyone. This is Mudassar. We will resume. Just trying to recall where we had stopped. Maybe we can just start out from here and then see where we meet up. Okay, okay, cool. Cool. So welcome once again. We have gone through a lot of things. Quorum is part of the leaderless replication. And we have this kind of a convention of W plus R greater than N by 2, that sort of thing. So let's go ahead with the limitations and then we move ahead. So if you have n replicas and you choose W and R such that W plus R greater than N, you can generally expect every read to return the most recent value, return for a key. So this is like the minimum number of writes, minimum of reads, uh, the greater than the number of nodes available. Okay, this is the case because the set of nodes to which you have written and the set of the nodes from which you have read must overlap. This is among the nodes you read, there must be at least one node with the latest value. There's a figure 511. Let's quickly have a look at it. Yep, this is the, yeah. So this is something we should fairly remember things, wherein we can see that W is 3, R is 3. So W plus R, which is 6, is greater than 5. So that ensures that at least one node will overlap and will have the latest value. Worst case scenario, if the two nodes go down. So that's the whole deal about W plus R greater than N. Often R and W are chosen to be a majority more than N by 2 of the nodes, because that ensures W plus R greater than N while still tolerating up to N by 2 code failures. But quorums are not necessarily majorities. It only matters that sets of nodes used by the read and write operations overlap at least one node. Other quorum assignments are possible, which allows some flexibility in the design of the distributed algorithm. And as everyone knows that, guys, if you're not following or anyone has any issues, please voice it out. We can discuss and have an open
I have
discussion.
one question.
Yeah, go ahead.
Uh, so when you say W R are chosen, so I assume I'm pretty new to this discussion. So I assume W is the minimum number of nodes for which you have to do write to call a write to be successful, and R is the minimum number of replicas that have to be consistent for you to return a read that is successful. Is that correct, or is it something else?
Yeah. I think it's correct. To be more precise, the way I remember is number of minimum nodes needed for acknowledgement. When if the
Acknowledgement.
right is,
Yeah, correct.
yeah,
That's the
the
word.
right to be,
Acknowledgement.
yeah, right to be successful or read to be successful. That's like the acknowledgement aspect where the W and R comes into picture.
Okay. Okay.
Okay. Okay. Moving
All
ahead.
right.
Yeah. With a smaller W and R, you're most likely to read stale values because it's more likely that your read did not include the node with the latest value. On the upside, this configuration allows lower latency and higher availability. If there is a network interruption and many replicas become unreachable, there's a high chance that you can continue processing reads and writes. Only after the number of reachable replicas falls below W or R does the database becomes unavailable for writing or reading respectively. One point is very clear that we understand right now. If W and R are less, then the stale values will appear. I think that is very clear because it's more likely that you didn't read or did not include the load with the latest value. But there's a positive side which is being highlighted over here. If W or R is less, is that there is lower latency and higher availability. I believe that you guys can chime in and correct me if I'm wrong. When it says lower latency, it's because one of the nodes is decreased, where it had to maintain, now it's less. And since it is lesser
Yeah.
number of there's high availability.
So, but it will not guarantee higher availability, right? Let's say you have 3 replicas. If one of the replicas go down, you still have availability on 2 replicas. So if you have lesser number of nodes, how does it guarantee higher availability? That's a bit confusing. Smaller is he talking about smaller value of W and R having higher availability? Okay. That depends on the definition of availability, I think. So in the standard definition, he'll say probably that the system is available if at least n/2 nodes are up and running and W and R satisfy the n condition. Did you get my question?
Yeah. Your query is that how does lesser
Hmm.
W and R help in achieving higher
Hmm.
availability? Lower latency, I think so. We are good because
Yeah.
it's lesser number of nodes
Yeah.
being read.
Correct. So consistency is lost, right? So definitely you'll have higher availability because now we don't need to take care of the quorum, right? Even if one of them is giving you the value, whether it is
Uh,
stale or it will return it, right?
Correct. So
So that's
you are
right.
trading
Correct.
consistency for availability here.
Availability. Yeah.
But even then, let's say if we take our use case where we say W is 3, R is 3, 6. Now let's say we make it less. We make it 2 and 2. Uh, but here we are still claiming that it needs minimum 2 nodes to acknowledge the read to complete. So it's just that one node has decreased, hence the acknowledgement cycle has decreased. Unlike it, if it would have been asynchronous, then that's a different thing altogether, where it's not waiting for the acknowledgement, it just goes and says that it's done. Um, so that's where I'm
So,
attributing the higher. Yeah.
I mean, it's W plus R has to be less than N, then only you'll read the stale data, right?
Correct.
Uh,
Yeah, he explains that in the next step. If you read through after availability highlighting, if there is a network interruption and many replicas become unreachable, there is a higher chance you can continue processing reads and writes. So the statement is confusing because we don't know if he's talking about lesser value of W and R or higher number of W and R. So we are interpreting it wrong, I think. So he means he ends the statement there where this drop with smaller you can have this, but on the upside you can have less consistency with W and R, but instead if you have higher number of W and R, you will have higher availability. So how about we interpret it that way? Because the explanation seems like you want higher number of nodes for higher availability, right? So that statement is ending there. On the upside is about having higher number of replicas which satisfy W and R condition. If we interpret it that way, then lower latency. I don't know how lower latency is guaranteed though. Higher availability is satisfied. How is lower
yeah,
latency satisfied?
it will be lower latency only, right? When you get a read request, you won't be checking in all the 3 replicas of read, right? Even if one of them gives you, you'll return it fast. So latency is reduced in that case, right?
In which case? So latency is reduced when you have less nodes or more nodes?
less nodes.
Then
Let's
less
say
nodes because your less nodes are required for
But higher
acknowledging,
availability.
isn't it? Yeah.
Higher
yeah.
And that also turns out to be a high availability because you are actually looking for lesser number of nodes for read as well as write.
But consistency won't be there. Yeah.
Okay, okay. All right. Makes sense.
See, when we talk
So both
about
are
stale values, then the consistency is not considered here, but they are saying that you will still get benefit of lower latency. So wherever you have such a user scenario, you can use it.
okay.
Hmm.
Sounds good.
Cool, cool. Um, I definitely see the upside to it, but I feel it's a more of a fractional or a minimalistic benefit here. It's not going to be significant of higher availability. Uh, just a thought though.
Yeah,
But
this is
nevertheless, yeah, yeah, Eric, you're saying something?
no. I was saying actually, this is how the Amazon's that cart application, right, works.
The Dynamo, yeah.
Yeah, Dynamo. That's basically they their application can sustain stale values, so they're okay with that. But a lot of the other applications probably won't be able to do this.
So a stale value in Instacart could be something like you removed something from your cart, but you still see in the cart, or you added something in the cart, but you don't see in the cart. So
Exactly.
it's not a very big deal to miss an item. So consistency is not needed, but user is not okay if it takes 5 seconds to add an item to cart rather than it being just instantaneous. So you can have faster response times and higher availability than consistency. So that's the use case there. All right.
Good, good. Yep. So that's that. Moving ahead. However, even with the W plus R greater than N, there are likely to be edge cases where stale values are returned. These depend on the implementation, but possible scenarios include possible scenarios. Okay. If a sloppy quorum is used, you'll see later on, the W writes may end up on a different node than the R reads. So there is no longer a guaranteed overlap between R nodes and the W nodes. Okay, because the writes may end up on different nodes than the R reads. Okay. Okay. But then overlap is happening, right? Why would it say?
No, what happens is actually in a leaderless system, right? You can send your write request to any node which is closer to you. So, but actually the actual node that the nodes that are going to store your data will be completely different because you have to hash that key and put it into a different node actually, right? But actually, let's say one of those nodes, let's say your replication factor is 3, and one of the node is down in the 3 nodes. The coordinator will store that information as a hinted handoff for the hints. But when the read comes in, actually, the coordinator won't participate in that read request. Only the 2 up nodes will be participating, right? And if you have the setting of quorum, right? Quorum means actually 51%. So let's say 51% of the, in this case, actually 51% means actually if there are 2 nodes up, then all 2 nodes has to respond.
So this is on the basis of the context that one of the nodes is down, like the overlapping node could be down. So in that case, it's a completely write and read nodes.
Yeah.
So
actually, all these systems want to have high availability, right? To high availability meaning actually they should accept the writes all the time.
Yep.
To do that, actually, the coordinator node or the node we are sending the write request to will store that write for that node that is down. That is the hinted handoff. But actually, that node will not participate. That coordinator node will not participate in the read request.
Thanks, Eric, for that. Okay. Moving ahead, if 2 writes occur concurrently, it is not clear which one happened first. In this case, the only safe solution is to merge the concurrent writes. If a winner is picked based on the timestamp, last write wins. Writes can be lost due to clock skew. So, yep, concurrency is another problem that can happen here. If a write happens concurrently with a read, the write may be reflected only in some of the replicas. In this case, it's undetermined whether the read returns the old or the new values. Okay. The write happens concurrently with the read.
So why that is? I mean, if both read and write happens parallelly, right? Then only write is reflected on some of replicas. Why so? Like few of them are dedicated for the read or what? Is it?
So actually this system doesn't follow the concept of linearizability, right? Linearizability is that concept that says actually the last write should be reflected on the latest read.
Yeah.
Yeah. So to do that, actually, you have to follow. Actually, probably you need a leader-based system. Normally, they do it using a leader-based system. Since this is leaderless, actually, you cannot guarantee that your last read will get the latest write.
Something like
So
read your own writes.
Is it because that the replication is ongoing on the other nodes? That's why it's not coming on all the replicas.
Yeah.
Because,
So let's say there are 5 nodes where you're replicating, right? So the write only replicated to 2 nodes in that 5. Right. Actually, at the same time, read comes in. Read request got the quorum from the other 3 nodes that it didn't replicate. Right. In the previous example, right? Actually, write only went to the 2 nodes. It is still waiting for the 3rd node to be done.
Okay.
In that case, actually, yeah.
So is that basically a delay of the replication waiting to happen on the 3rd node? During which before that write happens, the read is being done on the 3rd node. That's why the consistency is not there on the reads. I hope that was the same thing. Eric, that's the same thing you're saying, right?
Yeah, that's the same thing actually. Yeah, if you can scroll up to that picture, that would be easier. You can easily see that if you want. Or if I already understood, yeah, here, right? So the write only replicated to replica 1 and 2, right? So it is still, the message is in transit to replica 3, right? For the write, but actually read was faster. So read it from replica 3, 4, and 5, because you need the quorum, right? It satisfied the read quorum. Replica 3, 4, and 5 satisfied the read quorum, but actually the write was still going on to the 3rd replica.
Oh, so it will give the state values. 3 will have the state.
Clearly.
So is that, but again, it's for that moment where the replication is not done. But if let's say the read comes after a certain time post the replication, then it will start getting the updated value.
Yeah.
Yeah, but
so, go ahead.
No, I'm saying here read and write both are coming parallelly, right? In that sentence, what we are reading, write and read both are coming concurrently.
Yeah, but one thing is not leaderless always going to be having a consistent hashing ring. So if it is a consistent hashing ring, so it will always go for the first 3 replicas starting from the coordinator node, right?
No, the write request, the replication happens in parallel, right? Either you can do that way, the one you said, like actually the first you forward it to the first node, then it forwards to the second node, right? Then actually you have that extra latency issue. So what normally the coordinator node is actually, if there are 5 replicas for that key, actually the 5 writes will be sent in parallel, like in this picture that let's say that person standing next to that right tag, right? Let's say that's a coordinator node. Coordinator will send it to 5 replicas in parallel.
Yeah, but if we assume that replica 3 has the right value, yeah, our read request from the user will be able to understand that it should return this proper value because it was written. It has the newest timestamp, no? It's not clear why we cannot understand that which value to return.
So the replica 3 didn't get the right yet, right?
Okay.
Yeah. Because in this picture, it is showing what we are telling is actually replica 1 and 2 only the right went actually. Let's say that there is a network delay and the replica 3 still didn't get the right yet. But
okay,
actually
but it means, sorry, but it means that value is not committed, yeah? User has not finished his write request. We should not return it.
Oh yeah, so the request and write, the write and read request are in parallel, right? Actually means actually they are concurrent.
Yeah. So they're happening. It's
the same
a scenario. Yeah. Okay. Okay. Yeah. Makes sense.
Okay. Thank you.
Right. Cool. Okay. Then the next one. The write succeeded on some replicas but failed on others. For example, the disk on some nodes are full and overall succeeded on fewer than W replicas. It is not rolled back on the replicas where it succeeded. This means that if a write was reported as failed, subsequent reads may or may not return the value from the write. I guess it follows a similar example, but here it's a failure rather than the lag or the delay. There are specific dots that there's a failure and hence they don't return the expected value. Although they also mention here that overall succeeded on fewer than W replicas, it is not rolled back on the replicas where it succeeded. So yeah. Cool.
But in transaction, it is rolled back, right? Once we do any transaction and
there is no transaction here, right? This is leaderless, right?
Leaderless, yeah. That is in like SQL. Leaderless.
Interesting point here. Even though not a transaction, but when we say W is equal to 3, let's say W3 R3 kind of a scenario, considering that one is down, it would still not fulfill the overall acknowledgement, right? It needs minimum 3 nodes for its successful acknowledgement. So that either, I don't know if it's a case where the read repair happens till it waits for the third node to come up and then send the acknowledgement back, or will it send the acknowledgement of the failure back stating that, hey, I wanted 3 nodes to confirm, but I just got 2 nodes. The third node failed for me.
Normally, let's say only out of let's say 3 replicas needs to be 3 nodes to acknowledge, right? And let's say 1 is down. The coordinator node will take part as the third node and it will store as the hint. So the write will be successful.
Okay.
Okay, right. Then actually, when let's say in Cassandra world, 3 hours is the time when you say actually the node is permanently down or not, right? Within 3 hours, if the node comes back up, then this coordinator node will replay all the hints it stored actually. That way, the third node will come up to date. Let's say the coordinate that third node is not again didn't come up in 3 hours, then it is considered permanently down by Cassandra, right? Then all these coordinators nodes will expire all the hints it stored. Now the next way to bring it up is actually using that read repair, actually that Merkle tree logic.
That is anti-entropy, right?
Exactly.
But the read repair will be like when you actually look from other replicas and you actually get from all the replicas and some of them are not updated. So then it will I start updating the older replicas.
Yeah.
So that will happen as a read repair, right? When it is reading.
Yeah.
So if that also doesn't happen because you are not reading the value which you have written, so there will always be some, what you say, difference between the replicas. And at that time, you can use a Merkle tree to bring those replicas in sync.
Yeah, all these things are called anti-entropy mechanisms, right? Actually, anti-entropy, it can follow any of these, right? The read repair is one. The other thing is actually the hindered handoff is another one. The Merkle tree is another one. It depends on actually how much time, what is the time actually, right? If the read is happening before any of these, that read repair will take care of that. If that key is never read, right, then read repair will never happen.
Right.
So the next available best option to fix this is actually maybe the Merkle tree.
Yep. Because the Merkle tree way will take some time because you will do everything, right? So read repair is faster. Yeah.
Exactly. Last resort is the this read repair. Sorry, the Merkle tree thing. The read repair works for the keys that are frequently read.
Yeah.
But actually, if the key is not frequently read, then there is no way actually read repair can fix it.
Yeah. Yeah.
Okay. So I get the part when you say that there's a coordinator node that will take the place of this third node and make it work. Let's say if the W was 5 and there are 2 nodes which are down. So normally, do we have multiple coordinators or just one coordinator?
No, in that case, right, if if the replication is 5 and 2 are down, then you are good. Still, you have a quorum of 3. You don't need the coordinator node to take care of that, right? Let's say out of 3 replica nodes, 3 are down. Now you are out of quorum, right?
Okay. No, I was saying if W is equal to 5 as compared to the example stated over here for 3. If W is equal to 5 and 2 are down.
Yeah.
So
then it won't. It won't.
It won't, right? It would be a failure as an overall acknowledgement.
Exactly. There won't be multiple coordinators. There is only one coordinator. Whoever the client is connecting to, that will be the coordinator.
Good. Thanks, Sir.
And how does client know? Jupyter tells to the client that this is. I mean, how does the client know that this is the coordinator node?
No, so let's say you have a client. There are a couple of ways you can do it, right? Let's say we expose a DNS entry, right? The DNS can map to that node, or maybe another way is actually there's a client application or a driver which we provide to our clients. That driver knows actually what it needs to connect to. There are multiple ways you can tell.
Oh, I thought in Zookeeper something.
Yeah, that is another way actually. Whichever way actually, there are multiple ways you can do it. Normally, it's a DNS is the easiest way, because when you type www.google.com, right? Actually, DNS is routing us to the closest server we connect to, right?
Connect, yes.
Yeah, but if it is a consistent hashing ring, so anywhere the request can land. So in some cases, wherever it lands, then it will forward to the right coordinator node. So because each and every node will have the information of each and every other node, based on the gossip protocol.
It is not forwarded, right? Let's say you connected to one node in the ring, right? Then that node is the right coordinator for you. There is no forwarding.
Yeah, so there are 2 cases. One is that way, and the other is like whenever your request lands in, you actually take the hash value and then directly direct your request to that particular node. So I think the Dynamo does that way.
Okay. Yeah. I was talking about Cassandra's way actually.
Yeah, Cassandra does it different way.
Yeah. Then there is
if the data is not found in the coordinator node, it will take those many hops to reach to the desired.
It's only one
node,
hop,
right?
Yeah, there's one extra hop.
Yeah, whatever. Yeah. Either.
So not exactly. Not exactly one, right? The whoever was saying earlier. Let's say actually, let's say the coordinator for the data we are writing, right? that is a completely new node joined the cluster. This coordinator node didn't get that information yet. Let's say we are using gossip protocol. The gossip is taking some time to propagate. So in that case, what this coordinator can do is actually, coordinator knows actually where, somewhere actually in the ring, I know where this node should be, right? Because I can take the hash of the key and tell actually somewhere close by, I know where this data will be stored. But I don't know who exactly is going to store that. What it normally does is actually it will forward it to the last known person. So the gossip protocol will tell actually there is somebody in the ring somewhere close to that node who knows about this node. So it doesn't properly say that maybe one is the best case. Actually, it can go maybe more than one actually. Does it make sense, or am I confusing you guys?
Yes, it makes sense. Yeah.
Yeah, because actually let's say gossip is taking longer actually that.
But every node has a routing table, right?
Exactly. How the routing table is updated, right? There are a couple of ways. One is gossip and one through maybe a zookeeper, right?
Correct.
Cassandra is completely decentralized, so it doesn't use the zookeeper.
Okay, so via gossip protocol it updates the.
Yeah. It's more of an edge case actually. Yeah.
Corner case.
Right. Moving forward, if a node carrying a new value fails and its data is stored from a replica carrying an old value, the number of replicas storing the new value may fall below W, breaking the quorum condition. Valid use case. I hope everybody is getting this part. Even if everything is working correctly, there are edge cases in which you can get unlucky with the timing, as we shall see in linearizability and quorums. Thus, although quorums appear to guarantee that the read returns the latest written value, in practice it is not so simple. Dynamo-style databases are generally optimized for use cases that can tolerate eventual consistency. The parameters W and R allow you to adjust the probability of the stale values being read, but it's wise to not take them as absolute guarantees. In particular, you usually do not get the guarantees discussed in the previous area. Reading your writes, monotonic reads, consistent prefix reads. So the previously mentioned anomalies can occur in applications. Stronger guarantees generally require transaction or consensus. We will return to these topics and 7 and 9. Moving forward, I hope there are no questions or queries so far, or if they are, I think they are addressed. Okay. All right, moving ahead. Monitoring staleness. From an operational perspective, it's important to monitor whether your databases are returning up-to-date results. Even if your application can tolerate stale reads, you need to be aware of the health of the replication. If it falls behind significantly, it should alert you so that you can investigate the cause. For example, a problem in the network or an overloaded node. For leader-based replication, the database typically exposes metrics for the replication lag, which you can feed into a monitoring system. This is possible because writes are applied to the leader and to the followers in the same order, and each node has a position in the replication log, the number of writes it has applied locally. By subtracting a follower's current position from the leader's current position, you can measure the amount of replication lag. I believe everybody is getting this paragraph here, where it says that we have a replication log, and since the order is maintained with leader and the followers, we can always subtract the follower's current position from the leader's current position to get the replication lag. Right? However, in systems with leaderless replication, there is no fixed order in which the writes are applied, which makes monitoring more difficult. Moreover, if the database only uses read repair, no anti-entropy, there is no limit to how old a value might be. If your value is infrequently read, the value returned by a state replica may be ancient. Okay, so interesting stuff when they say this. So leader is no ordering. So since there is no ordering, monitoring is difficult. Now I don't know if it's just difficult or impossible here, but it says that it only uses read repair. So it's basically purely on the basis of how successful the read repair happens. If the read repair does not happen, then it's, as it said over here, it might be an ancient value still sitting on that replica. Uh, in case of leaderless replication. So can I say this for leaderless replication? In case of the replication lag can be addressed with the help of only read repair. Is that statement correct?
No, the other way, right? You should have anti-entropy can help you with that.
Okay, but here it says if the database. Oh, sorry, my bad. I missed this part. Here it says that if the database only uses read repair, I think that's more of a use case based database or a vendor based database where it says that it only uses read repair, then it could be a more older value.
Yeah. So basically, you can turn off that feature, right? Normally in databases, the anti-entropy features, right?
Oh, really? Can be?
Yeah.
I didn't know that.
Yeah. Cassandra, you can turn off this sloppy quorum, all those things actually.
Interesting.
Yeah, plug and play option.
Okay, that's cool.
I think there is an
Also,
entry in
Sasang
the...
name. Sasang, your name is there. Hinted hand up.
Yes.
So, but if you turn off the sloppy quorum in Cassandra, what benefit do you get? It's only latency.
Disadvantage you will have, I think, right?
So let's say the sloppy quorum, right? So the issue is that's an extra storage requirement for this coordinator node, right?
Mm-hmm.
There is the latency. Then after the node comes back, this guy has to replay everything. There is a network issue. It depends on the use case. How do you want to do it actually?
No, I was just wondering whether there is a use case like that, because you still want the data to be, synced up, isn't it? So the number of replies.
Let's say your keys are pretty much read. Let's say you have a read-heavy network, right? And write-less and read-heavy.
Okay,
So whatever you write is already almost all the time it is read, right? Then that's an extra thing, right? Your keys will be always repaired by the read repair.
Okay, makes sense. Yeah.
Could be like your system does not require the high availability, but you are inclined towards the consistency. So that could be one of the reasons.
Mm-hmm.
Yeah.
So because Cassandra is also more high availability on the right?
Yeah, because then if you have this sloppy quorum, so your write may succeed, but read will still show you the old value.
Mm-hmm. Okay.
Cassandra never says that. Right? It says actually it's tunable consistently. That's what they want everybody to say, right?
Yeah. But basically they come from the Dynamo, an enhanced version of Dynamo. So you always think that way. Yeah, they have that. Yeah, that is true. Yeah, go ahead.
Yeah. Cool. So good stuff knowing that. Moving ahead. There has been some research. There has been some research on measuring replica staleness in databases with leaderless replication and predicting the expected percentage of stale reads depending on the parameters NW and R. This is unfortunately not yet common practice, but it would be good to include staleness measurement in the standard set of metrics for databases. Eventual consistency is a deliberately vague guarantee, but for operability, it's important to be able to quantify eventually. It's a very interesting point it has mentioned. How that yes, we all keep saying that should be eventually consistent, but then how do we quantify that, right? That's where the stateless measurements might help. Interesting stuff.
So if they say the parameters are just N, W, and R, but still there's only 3 parameters are actually interpreted so many ways, and it makes things so much complex, isn't it? So there are so many combinations.
With 3, yeah. And RWNLU play.
But actually in Cassandra and all, actually they don't say NWR, right? They say 1, 2, then quorum, then all or something.
Yeah, they have the big list.
Yeah.
All also
Or
only
then
one.
Exactly 1, yeah. At
Yeah,
most.
And cross
then-
data center also.
Yeah, then they have local quorum.
Yeah.
Yeah.
Cross quorum. Cross quorum is also there, right? Across the 2 data centers.
Yeah.
I didn't hear about the cross quorum. Yeah, I'll take a look.
There is.
Okay.
You have a data center. You can have a node outside it.
Okay, gotcha.
Okay.
Global quorum, we say something like that. If I...
Mhm.
Okay.
Yeah. So do you want to do the sloppy quorum?
Yeah, I was just wondering, should we start now or should we start next time?
Next would be fine, right?
Because we already have a hinted ad of here, so you can ask him.
Sure.
Yeah,
Yeah,
we
let's
can
start.
have it.
Yeah.
Okay, let's start.
Let's start next time and let's see.
Yeah,
New
because this
topic
is a
also.
big topic actually, isn't
Yeah,
it?
it's a big topic.
Correct.
And we want to do it better this time.
Yeah, we might take a little more time maybe just to cover it, but starting maybe tomorrow would be a good practice.